Good morning, good afternoon, good evening. Welcome to another IWS webinar. Thank you for joining today. It's my great pleasure to welcome our speaker today, Alessandro Bettin from Hitachi Water, Europe. He is going to talk about how to deal with intermittent water supply using systematic approach. Before I hand over to Alessandro to introduce himself and give his talk, I'd like to remind all our participants that you can add your questions in the chat. At the end, we are going to have a Q&A session and Alessandro is going to answer your questions. Thank you.
So thank you, Razia, and welcome to all to this webinar. I introduce briefly myself. I'm a civil engineer with 30 years of experience in water management projects, non-revenue water project. I'm business development advisor for Hitachi Europe Water Management Division. The focus of the presentation is how to fix intermittent water supply using a systematic technical approach. 2 case studies will be presented where this systematic approach is being successfully implemented. So first of all, some general consideration. What is intermittent water supply? Intermittent water supply is related to pipe water supply service that is available to customers less than 24 hours per day. It is estimated that 1.3 billion people around the world, mainly in low and middle income countries, are affected by IWS. Customers usually secure their water supply using ground or roof tank that fill the water when the supply is in charge. A special situation is when we have temporary intermittent water supply. This is due to unexpected reasons like drought, pollution of water resources. And this reason brings to the shifting from a continuous normal supply to an intermittent supply. And there are several cases of this kind of situation. And if not resolved quickly, a temporary emergency can easily turn into a permanent intermittent supply with all the negative consequences in the network integrity. Why intermittent water supply is globally increasing? There are several reasons. The first is increasing water scarcity. Due to changing precipitation regimes caused by climate change, the period of drought are more and more frequent and are most of the time followed by floods. And this situation, of course, is very negative for the water supply. And water operators sometimes have to shut down the water, mostly overnight, in order to cope with the new emergency situation. We have also another reason, that is the continuously increasing of demand. Water demand has tripled globally during the last 50 years. It is expected to increase 20 to 30% by 2050. Urbanization is also increasing. More than 50% of the world population live in urban areas, and it is expected to rise to 68 by 2050. Last but not least, there is a huge amount of water loss worldwide. It is estimated that more than 340 billion liters of water are lost globally from drinking water every day. So which are the main characteristics of a network affected by intermittent water supply? High level of leakage. We can have a level of leakage even higher than 50, 60% of the input volume. Low pressure, generally low pressure, even less than 10 meters. We have air in the water pipes. Air in the water pipes is entering during pipe filling when the valve is opened. For example, the valve of the reservoir is opened to fill the pipe. Pressure transient due to the filling empty of pipelines under intermittent supply. And due to pressure transient, we have a normally high burst frequency, so a high level of natural rate of rise of leaks. Let's see which are the air problems in water pipe. First of all, air generates problems of pressure transient. We will see that the small accumulation of air inside the pipe can have adverse effect on pressure transient, increasing the magnitude of the transient. Then we can have flow reduction. Flow reduction is determined by the air pocket that standing in the pipe can reduce the effective pipe cross-section. And it is a reduction in effect of the pipe capacity. We have greater erosion for metallic pipe, for ferrous pipe. The presence of air increases the corrosion by making available more oxygen for the oxidation process. Then we have a pump efficiency reduction, as can be seen from this picture, due to the higher heat loss. If the main line has air inside, the pump pressure has to be increased with losing of efficiency. And finally, we have also a potential for flow metering errors, because air bubbles in some cases can inhibit the propagation of ultrasonic waves in ultrasonic meters. So let's see now air origin and transport in water pipes. We're still speaking about theory. We know that at normal temperature, there is a 2% saturation level of dissolved air in the water. But with low pressure and high temperature, air come out of solution and accumulate in the system. Air inlet and transport is determined by filling emptying of pipeline, and this is a typical situation of IWS. There are several kinds of air pockets. Air pockets can be transported with the flow if the gradient is small, but can also be trapped with the steeper pipe gradient. And we can see from these two pictures, the upper picture, we have an air pocket in an horizontal pipe, and it is elongated and very thin. While in the other picture, we have an air pocket with a wedge-like shape, and it is a steeper slope pipe. Let's see now the effect of air pockets of various volume on pressure transient. After the pump shutdown. This is an experiment carried out. And we see that there is a transient where three conditions of, so we have the first condition is no air, and it is the continuous line. It is this one. Then we have the volume of air of 0.7 cubic meter, and it is this one, this line. And then we have smaller air bubble, smaller air pocket, that is this dot line. So we can see that air pocket can be beneficial or detrimental depending on the volume. So a big volume reduces the effect of pressure transient, big volume of air, while a smaller volume of air increases the effect of transient. You see, there are seconds. So it can be seen that single air pockets with small size and multiple presence of air pockets in the pipeline are shown to be problematic without any protection. So they are going to increase the effect of the normal pressure transient. So after this introduction, above all on the pressure transient and their effect, let's see in detail which is the systematic approach that can be carried out to bring an intermittent water supply generally a temporary intermittent water supply to a 24/7 continuous supply. So we have several stages. The first one is a situational assessment, where we need to assess network analysis. We need to check if there is enough water available to satisfy demand. We have to measure the leakage in the system and also carried out monitoring of flow and pressure. Then second stage is implementation of district metering. Then we have air control and pressure transient control. As we are seeing, air is detrimental for the functioning of the water supply system during intermittent water supply. So the task is to select the suitable position to install air valves in order to reduce the pressure transient. Then an important stage that has to be carried out together with district metering is the pressure management. So design of pressure area isolation, and selecting the right pressure reduction value. It is very important to optimize and to reduce pressure in an intermittent water supply network. Even few meters of pressure reduction can have a high benefit in network stabilization and in the distribution of water to the different areas. Last stage after pressure stabilization is a leak detection. So leak pinpoint and leak repair. As you can see, the process is not linear, but need continuous testing and verification until the result is achieved. For example, if after a leak detection campaign and repair, continuous supply is not achieved, it could be necessary to come back to the previous stage and maybe implement a new setting in the pressure reduction valve, because after leak repair, pressure normally increases, and then we can decrease a little bit more the pressure. And if this is not enough to have 24/7, we can go back again and check air control. So it is a continuous test and try process. At the end, maybe a new leakage detection campaign can be beneficial and can be effective to bring to 24/7. It is not an easy process, and it is not a linear one. Let's see now one by one in more detail the several stages. So situational assessment. First of all, we have to know the network. So it's very important to build the network schematic, how the supply is generated, and to collect all the data necessary to carry out the water balance, because leakage estimation using the minimum night flow, that is the standard method, most of the time is not possible with the intermittent water supply, because during night the service is shut down. If we don't have the data from this SCADA, we have to measure the flow, and in any case, flow and pressure monitoring is mandatory to understand the network, and then carried out the water supply, the water balance, for example, for 1 week to week, if we don't have any other data. And of course, we have to evaluate if the available water resources is enough to satisfy the demand. Second stage is district metering. District metering is the most reliable methodology to carry out an effective non-revenue water control in the system. Normally, the network is divided by sectors, possibly fed by only 1 meter, but they can be 2 or 3. And the sectors are created, closing the boundary. The flow in each sector is measured, and in this way it is possible to quantify leakage in each Dma. Air pressure transient control. After the creation of Dma, and we have to make an analysis of the pressure transient, and selecting some suitable point to install this air valve in order to eliminate this extra air inside. Air valve should be considered to reduce the pressure transient effect, and they have normally triple actions: evacuate air bubbles in normal condition, evacuate air pockets and large volume of air that is trapped inside the pipeline, and introduce air in the system to prevent vacuum conditions. They should be installed where a flow variation is expected, for example, at the outlet of a pumping station, at the outlet of a reservoir, where the opening and closing valve is activated to fill the pipe, and in height spot. Other valves that are useful to calm the network are pressure release valve, and they protect pipelines against overpressure due to sudden changes of regime in the network. For example, downstream a pumping station in order to prevent water hammer and transient. A very important task is pressure management. Leakage rate is proportional to pressure, and if we reduce pressure, we reduce leakage. So it is a very cost-effective way to reduce leakage, to implement a pressure management. There is a physical relationship between leakage flow rate and pressure, as you can see from this chart. And the power factor N1 of the formula varies from 0.5 for metallic pipe and 1.5 generally for plastic pipe. In a standard design situation, we can consider an average value of 1 in order to estimate the affecting leakage from a pressure reduction in the system. Best pressure zones are characterized by only one inlet where a flow meter is installed and where a pressure reduction value is installed. There are several benefits from pressure management. Of course, reduce of leakage, reduce of burst frequency, and protection of assets. This is an example of a pressure management implementation. It is a case study in Italy. And we started from 80 meters of pressure. It was a lower district, a small lower district with a very high pressure. And a pressure reductor has been installed. And the first stage was to bring from around 80 to 45 meters. And we obtained suddenly 30% of leakage reduction. And then with a further setting to 35 meters, constant all the day, we had 40% of leakage reduction. This is another case study where we can evaluate the combination effect of pressure management and leak detection. This is a case study in Sardinia, in Italy, where we had a reservoir feeding 5 Dmas, and in 4 Dmas, as you can see, 4 pressure reduction valve has been installed with a day-night setting, and the average pressure reduction was 15 meters. And the effect, or the only effect, the effect of pressure reduction is 60% reduction in the minimum night flow, and therefore in leakage. This is a daily chart of flow, of the total flow. And then after pressure reduction, all the leaks found has been pinpointed and repaired, and we obtained a 50% further reduction. So at the end, the combination effect brought the minimum night flow from 30 liters per second to 11 liters per second, stabilizing completely the pressure. The last stage of the methodology of the systematic approach is leak detection. Leak detection is very important because it is the final step, and if it is well carried out, it can bring to very important results in terms of minimum night flow reduction. leak detection is characterized by a first task that is leak location that can be carried out implementing step test analysis in the network in order to find high leakage area, or noise logging. Noise loggers can be deployed depending on the network cost-benefit analysis in order to carry out an automatic sanding. Leak pinpointing is then generally carried out with the traditional activity that is sounding and correlation. The correlation used to pinpoint the precise point on the leak, and the sounding is just used to understand, to hear the noise from any fitting in the network in order to find out the possible location of the leak. Another technology that we currently used sometimes is a tracer gas to pinpoint difficult leaks in condition of low pressure. This is an example of how leak detection and repair can be monitored in order to evaluate the leakage volume recovered. So this is the time. There are the leaks, 9 leaks repaired with the point of each leak repaired, and we have the pressure, and you see, and in blue we have the flow, and we see the reduction of the minimum night flow. So 9 leaks repaired, and we measuring the difference in the minimum night flow after minus before the leak repair. We had evaluated 0.4 liter per second per leak and 35 cubic meter per day. So let's see now the case study from temporary intermittent water supply to 24/7. This is the first case study that I would like to show where the integrated systematic approach has been applied. We are in Norcia, Italy. Center Italy, there was a situation where, due to low precipitation, a strong decrease in available water resourcing has been experienced. And due to this situation, the operator shifted to intermittent water supply, closing the outlet of the reservoirs overnight in order to maintain the reservoir filled during the day. This is the network scheme. And this is the reservoir, this is the point of distribution. These are the Dma that then has been created. And initially, the situation that has been measured is represented by this chart. This is the pressure at this point. And you can see that we have a negative pressure in 2 episodes. It is 12 hours, this graph. So minus 3 meters and minus 7 meters. So probably there is the presence of an air pocket or more air pocket subject to compression, decompression that determine this transient, and even can determine also negative flow, because during the measurement of the flow, there are also some flow that are near to 0 or even negative. So the air was a big problem as an initial assessment of this system. Which are the activities carried out? We set up a 3DMA. We carried out the installation of air control valve downstream the reservoirs at another point of the network, suitable point. We set up 2 pressure zones with 1 inlet, 1 PRV at the inlet, and then 20 leaks has been located and repaired. There was an initial level of leakage very high, more than 50%. So you see here the setting of one of the PRV, day-night setting, different setting, lower pressure setting during the night when it is possible to lower the pressure. And this is a comparison between the 2 charts of the flow, the outlet flow at the beginning, when there was intermittent water supply, air in the pipe and pressure transient, you see the irregularity of the shape of the flow and the minimum flow during night when the reservoir is closed. And this is the result achieved at the end after all the implementation of these activities and this equipment, installation of this equipment. So it is a standard curve of a continuous supply with a minimum night flow of 6 liters per second. This is one of the 2 Dma. This is another case study. Again, we started from a situation of intermittent supply with around 10 hours of supply per day from 6 in the morning to 4 in the afternoon, and then everything was closed. We are in Vasto, south of Italy. 20,000 users were affected by this intermittent supply, and 80 kilometers of network, 3 reservoirs, 1 pumping station. So mainly the supply is by gravity, and again, a high level of leakage. So the objective here was to improve network efficiency and reduce leakage in order to achieve 24/7. 9 Dma has been set up, checked, boundary has been controlled and measured, 3 pressure zones created, leak detection carried out, sounding plus correlation, and 40 leaks repaired. One of the leaks has been found to be 7 liters per second, has been pinpointing along a main trunk feeding the reservoirs. Using, this was a difficult leak, and for this leak it was used a tracer gas after subsequent flow measurement in order to select the cross-section where the leaks were present. And you can see here the result of the flow of one of the DMA. So in red, we see the initial situation at 6 o'clock, the opening with the peak flow, and then the stabilization, then the closing, because the reservoir was completely empty. And then after the implementation of pressure management leak repair, we had a continuity of supply, of course, limiting a lot the flow, the average flow to 8 liters per second compared to before, that when it was operating the system was 17.5 liters per second. So it is very important in case like this, case of intermittent water supply, to optimize the pressure and to reduce the pressure, because even a small pressure reduction can give a very important effect in toward continuity of supply. We have seen the systematic approach. We have seen 2 case study application and other case studies to see the single phases. And let's speak about how digitization water network can improve efficiency. Today, there are a lot of data available at the water utility, several kinds of data. The problem is that all these data are generally spread in different sources, different formats, and different proprietary software. The solution is to integrate all this data into a common database and to use this data to create an intelligent system to support operation and investment. There are several benefits in that, also for network affected by intermittent water supply. So we can have an incident rate reduction, prompt leakage evaluating, pinpointing, and reduction, optimization of operation, and very important, more equitable distribution, because if we collect a lot of data and we know how the network is performing, we can optimize the sequence of distribution in a network affected by IWS, water safety improvement, and of course, targeted investment in order to maximize the benefit of the investment. With Hitachi, we are carrying out, we are implementing such a system for a primary water utility in Italy. And here you can see some example of some dashboard for the water supply system. One is for the water quality KPI and of course regulation activity, regular activity. This one is one of the dashboard that's been implemented for non-revenue water control and analysis and reduction with all the KPI. And the third one is a representation of the water production compared with the previous period. Intermittent supply and water demand. It is not always a matter of water quantity. Here we are in Pune, India, and I collaborated with the implementation of the detailed project report for transitioning to 24/7, and I was in charge for the part related to leakage management. And we carried out around 10 years ago a customer survey in some customers in India, domestic survey in some slum area for a period of 1 month about, and we found that the consumption per person per day was 190 liters per second. And of course, this is more than enough consumption. The water supply here was 6 hours per day. So situation is intermittent supply. The customers were not metered, and there was a high level of leakage. Now, as far as I know, they have started to meter customer based on consumption, so probably the situation is changed. And I would like to show another situation that is of course not comparable, but this situation, this is Copenhagen. This shows that the unit consumption per person can be lowered a lot. We have here 104 liters per person per day, only domestic, and the situation of the network is completely different, of course. Metered customers, low level of leakage, and also high water tariff, because the tariff is for sure a leverage to reduce consumption, but it is another discussion that probably can be done in another webinar. So we see that 104 liters per second is enough for a person, but even less. And this is to say that in order to fix intermittent supply, to bring 24/7, it is very, very important also to address the unit consumption. It is also very important to reduce consumption. So public awareness programs can be effective to achieve a reduction in water consumption and minimizing waste. This is again the situation of Copenhagen. And I would like to show you, because in my opinion it's very interesting, the decrease in water consumption experimented in Copenhagen during the last 20 years, from 1997 to 2016. And as you can see, the domestic consumption is decreased from 50 cubic meter per year to 38 cubic meter per year, with minus 25%. In the same period, the population has increased by 80%, 8.3%. But if we look at the green area, it is the consumption from business and the industries. It seems that there is not a big reduction, even if there is a small reduction in consumption. But if we compare this situation with the increasing of the GDP during the same period, we have an increase of the GDP of 80%. So if we consider the unit consumption per product, we can see that it is really decreased. And it would be interesting to compare this situation, that is of course one of the best situations in Europe, probably the best, with other realities, and to see how is the trend of consumption at water utilities. In an increasing water scarcity environment, a responsible use of water aimed at consumption reduction both for citizens and enterprise is necessary. So it is not only necessary to apply the right methodology and the right approach with the best technology. But in order to obtain a better result, it is very, very important to obtain a more equitable and water balance water distribution. This is the last slide. If you have any question, please fill the questions in the chat.
Yeah, thank you very much, Alessandro, for very interesting and informative talk. I don't see any questions at the moment in the chat. Please add your questions to the chat. While we are waiting for participants to ask their question, I've got a question. For the 2 case studies that you mentioned in Italy, converting from intermittent to continuous system, did you observe any changes in user behavior after that temporary intermittent water supply event?
Okay, the first case was a temporary intermittent supply. So no, we didn't evaluate any change because there was not the reservoirs. So the consumption, the system remained 24 hours. While in the second case, it was a long-term intermittent water supply. It was lasting for a year due to several reasons of poor maintenance, high level of leakage, and so on. And all the customers had the private tanks at home, and thanks to this they had the private tank, so we could lower the pressure because they had already equipped the private tanks and sometimes with booster and so on, so we could decrease the pressure a little bit more. But as far as I know, private tanks are still in charge because it's difficult that after 24/7 established, at least at the beginning, these tanks are deactivated.
Great, thank you. So we've got a couple of questions. The first one is Shashi Sikar, hopefully I pronounced that correctly, from India, and the question is, can you elaborate on intermittent water supply balance can be applied in intermittent water supply situation 2 to 4 hours in 3 days in developing countries like India, where metering is almost absent or not working? Should this methodology be applied in such situation?
Yes. So if the meter is absent, the customer meters, so we can have customer meter absent. So if the meter is absent, we estimate the consumption of the customers. For example, in Pune, we made a customer survey. And if the SCADA is missing and the measurement is missing, we implement direct measurement of flow. We install equipment, portable equipment, and we measure. In all the case studies that I show, we carried out flow measurement with our own equipment, portable equipment. For example, clamp-on equipment, pressure meters, and so on.
The second question is from Matthew, asking, how would you design the pressure management zones in the network? Would they be the same area as the DMAs, or would they be based on elevation?
Pressure management and DMA implementation should be carried out together, because when we design DMA, normally we try to design DMA that is also suitable for pressure management. And pressure management can be done only if the elevated point, if the pressure in the elevated point can be decreased, because we have a level of service and we have to guarantee a certain pressure. So both, I would say that the answer is both. Both the pressure zone are designed together with DMA, and then depends on the elevation also and on the pressure that can be available after reduction.
Okay, thank you. There is a comment from Alan saying that he's done a survey of 100 cities in Latin America comparing continuity and water use. The results shows no correlation. So a lower continuity did not increase or decrease.
Yes, this is a very important issue because intermittent supply, I mean, most of the time, in the case that we are seeing, and the water, if there is water available, intermittent supply brings the water to the population, and because they have the tanks, they can fill the tanks, and they can have even, some of them can have even more water that is needed. Okay, so the balance is the same. It's just a question of distribution.
Next question is, which method of leakage detection is more effective in low pressure, less than 20 meters?
Okay, less than 20 meters is, if we are around 15, 20 meters, we can use traditional acoustic approach, sounding and correlation successfully. And then if the pressure decrease under 10 meters, it is very low. One way is to use tracer gas.
Okay, thank you. Next question is regarding reduction in consumption during the temporary intermittent water supply period. Was there any reduction in the consumption during the operating as an intermittent water supply system?
No, there was not a reduction in consumption. There was a reduction in leakage because when the water available is not enough to feed the demand plus leakage. If leakage is very high and there is a lot of water, the water can be flowed into the system as much as possible. But when there is a decreasing due to temporary intermittent supply due to drought period, low water and so on, applying immediately the intermittent supply brings one immediate effect, that is reducing leakage, because in this way the consumption remains the same. Of course, if the situation is getting worse, the shutdown has to be longer and longer, but always reducing leakage, because having in the situation with the reservoirs, with the tanks, is the tank is filled, and sometimes people they also have two tanks, not only one. So it's we don't see a big reduction in consumption.
Okay, thank you. Next question is, there are expected climate change effects, increases in urbanization and water demand. In your work experience, have you noticed any matching planning efforts in developing countries to counter or mitigate the effects of these expected occurrences?
Climate change, of course, is increasing the problem, and I have seen in a certain situation that there was a real focus on public awareness to try to reduce consumption and to use the water in a more responsible way. Of course, urbanization is a big problem because a huge amount of water has to be ready available in a relatively small area. And, but the key point is for sure to reduce consumption and to optimize water resources, reduce pollution of water resources, and also there are other important activities that make water use, for example.
Yeah, thank you. So next question is, what was my question? Razia, referring to myself, my question was about reduction in demand consumption, which Alessandro answered that question. Next question is, can you suggest which is the minimum pipe diameter to be considered in design of 24/7 water supply systems?
The minimum, sorry?
Pipe diameter.
There is not a minimum pipe diameter in terms of absolute level. It depends on the network situation and the demand, the pressure. So normally, some networks are designed already to be intermittent when there are economic constraints. And of course, being intermittent, they have to have a larger diameter normally, because they have to bring the same amount of water in less time. Normally, the diameter depends on the demand and the heat loss, etc.
Thank you. Next question is, how many household meters in Hdma for better leakage management?
This is a good question. The standard methodologies say from 2,000 to 3,000 customers, okay? 1,000, 3,000 would be. It is the standard UK methodology, but according to my experience, it depends again on the size of the area where you are going to implement the leakage plan. If we have a big city, bigger area has to be considered. The smaller is better because it's better to monitor a small DMA, but to have too many small DMA is not cost effective. So probably a solution could be also to have a macro area and then divide this macro area in smaller DMA, maybe temporary DMA, to check where leaks are located.
Thank you. Next question is, what is the minimum pressure to be adopted for 24/7 water supply?
Again, it depends, because we have seen network with the pressure that was less than 10 meters, 6 meters, 7 meters, because all the customer had the tank with the booster. So it was just, the pressure was just enough to deliver the water to the first level floor, I would say. And depends, because if the citizens, they have the roof tank, the pressure has to be the minimum pressure to fill the roof tank. If they don't have any tank, the minimum pressure is the pressure of the most, of the higher point. So maybe the minimum level of service normally is a certain level of meters of pressure upon the higher user, maybe 30 meters, 35 meters. And this is in Italy. But again, with intermittent water supply, the pressure can be, and even bring it to 24/7 can be lower.
Thank you. Next question is, will there be any change in the working behavior of AMR meters in case of 24/7 and intermittent water supply? Few cases we observed during IWS, the meter starts working after few seconds of charging.
Yes, this is due to the air in the system, probably.
Next question. Sorry.
Yeah, the air in the system that brings errors in reading of the meters, even private customers' meters.
Okay. Next question is, in the situation assessment stage, is there a planning horizon attached when using the water supply demand balance. And this is in view of the ever increasing water demand.
Planning horizon touch when using the water supply demand balance. Yes. Of course, the water supply demand balance is very important because give a current picture of the availability of water compared to the water demand. And normally, as a rule, but again, depends on of each regulator, because these activities many times is characterized by the regulator. The water supply should be 20% more than the peak demand in the peak day of the year.
Okay. So next,
it means that, of course, we have to consider the demand plus leakage, the overall demand.
Yeah.
If the water supply balance is the value is lower, if there is a value less than 1, leakage has to be immediately reduced in order to bring the water balance greater than 1. The water supply balance indicator greater than 1.
Okay, thank you. Next question is, in your work experience with IWS, how have you incorporated pressure zones and DMAs where there is much unknown in these systems?
Yes, it is something that can be done. Of course, the more the knowledge of the system, the better it is, because we can have more precise design solution. But knowing the pressure of an area, it's a lot of field activity. There is a lot of field activity, understanding which are the right boundary of the area and the pressure that can be present in that area, the pressure that can be reduced, and the simulation of the pressure reduction can be done before installation of the valve on the field, just closing the valve. Closing the valve, you can simulate a reduction in pressure and see if it is okay, if it can work. Of course, the knowledge, the network drawing should be available, or if no data exists, it is necessary to carry out a site survey and to develop a GIS, because the first part is to know the network.
Yeah, in some cases, we have we are working on a couple of case studies. We have network data like hydraulic model, but usually the monitoring data is limited, or that's the challenge, how to calibrate those hydraulic models before using them.
To calibrate a model, a field survey has to be carried out. So portable flow meters, portable pressure meters, measurement of pressure transient should be deployed in the right position in order to have a good calibrated model.
Yeah.
It is something that for sure has to be done. Has to be done, sorry.
Yeah, thank you. And final question is, sorry, this disappeared. Was there a big difference in the maximum flow rate in the main pipe between IWS and continuous system?
Yes, we have seen in the graph before. It was let me check if I can recover the. Yeah, you can see here. So we had a peak of 40 liters per second here in with the peak when the opening of the reservoirs compared to less than 15. This is the typical morning peak. So it is a big difference. Much higher velocity. And then if you consider also the effect of the air inside the pipe can be really detrimental for the system, because the system is very stressed by this situation.
Great, thank you. And another question is there any methodology for assessment of existing network pipeline system in intermittent water supply situation? If not, what do you suggest?
For assessment of existing network pipeline system, do you intend for the assessment of the location of the pipe?
I think probably is referring in your graph, the first stage in your framework you presented, situation assessment.
Ah, sorry, situation assessment.
Yeah. Is there a methodology?
Yes,
to do
situation
that?
assessment is the first stage. So it has to be carried out very deeply and with experience, because it is the first step to move toward all the other design and implementation. So the first step is to visit for sure all the plants, reservoirs, pumping station, and so on, and to draw all the network schematic of these systems, to understand where the distribution happens, to locate the point for measuring all the flow. So the objective is to measure all the input flow from the network, from the Dma or from the sector that we are going to address. And normally, if the minimum night flow cannot be executed because maybe there is no pressure overnight, we have to implement directly the water balance. And the water balance, in the water balance, we can use the flow measured with our portable equipment, maybe for 1 week or 2 weeks. And we built a small water balance of only 1 week, for example, only 2 weeks. And for the same period, the estimation of customer has to be implemented, taking the data from the company, for example, from the billing system, or making just an estimation based on the population. And in this way, we can evaluate precisely the level of leakage. And one other important thing is that the level of leakage with the water balance, the water loss, has to be evaluated considering the real time of supply. And then make an extension, a comparison to arrive to 24 hours. In this way, we will see that leakage is much higher than what we expect.
Okay, great. Thank you very much. I think we are running out of time. Just quickly, last 2 questions. First one is about, could you please explain the gas leak detection method a little bit more?
Yes, gas leak detection is a blend of gas that is, of course, suitable to enter into the system. And this gas is injected through the, I would say, a pressure, a connection point, like, you know, the same connection point that is used to connect a pressure meter, and is injected in the pipe. Possibly the pipe should be almost empty, or anyway with low pressure. And the gas injected in the pipe, when finds a hole in the pipe, like a leakage, come back from the pipe and can be found by a receiver, okay, by a receiver outside in the road that can detect the precise point where the gas is received.
Yeah, and the final question is the reduction in the demand in a Copenhagen case study. Any reason for that? Probably
yes,
efficiency?
this is a very good question, and because, for example, in Italy we have much higher water consumption. I think that one big driver for that is the high tariff, because I know that they have a very high tariff compared to the average tariff of in Europe. And for sure, pay more the water the people is reducing the consumption, for sure. And of course, probably also a cultural reason, in my opinion, because there is also an awareness of in the saving of water resources and resources in general. And this awareness, in my opinion, should become mandatory for all of us.
Okay, great. Thank you very much. We have run out of time. Thank you very much to Alessandro for very informative talk, and thank you for answering all the questions. Thank you to all the participants for engaging and asking a lot of very important questions. Just before we leave, we have got a couple of announcements. Alessandro, could you please go to the next slide? So usually we get a question about previous talks. All the webinars are recorded and they are available from YouTube that has been set up for IWS webinars. So please visit our YouTube webpage where you can find all the previous recorded talks. Next slide, please. I would like to remind all participants that we have proposed a special issue for intermittent water supply system in Aqua Journal. This is open for submissions, and journal has proposed that all the reviewed accepted papers will be published immediately, so they are not going to wait until the deadline. So I would encourage all the participants, if you have got papers that are suitable for this special issue, please submit your papers as soon as they are ready. Don't wait for the deadline. And that deadline is for finalizing the special issue. And so the journal is going to publish the papers when they are ready and accepted. And final slide, please. As we mentioned in previous webinars, we are planning to do the monthly webinars last Wednesday of each month. We are going to have one webinar, so we have scheduled another one for 23rd of February. You will receive email regarding the registration link, so you can register for the next webinar as well. We also would like to invite you to propose yourself or anyone you think are active in this subject area. If they like to give a talk at one of our webinars, please contact myself or Joe Dalton. Our emails are on this slide, and we will try to schedule in our future webinar series. Thank you very much again for attending the talk, and thank you for Alessandro for his talk. Thank you very much, and see you at next webinar. Goodbye.